Hello everyone, I am David from LectureMate, and today I'll be giving you a speed run of AS Chemistry. Basically, I'll be going through the very common questions that you will get, and I'll be explaining how you can answer them. Note that I will not be going through every possible type of question. The video would be like 5 hours, 6 hours long if I did that. But I'm just going to go through the ones that are always that basically come out almost every year, either in the form I've given or in a slightly modified form. So without further ado, let's hop right in. Alright, before we actually start going through the common questions, I would like you to open this link in another tab. Why? Because most of the content I'm covering in this video is present on that website, and I'll keep referring to it as I go along. So please pause the video, copy out this link, it will be in the description, and put it out on another tab. As I'm going through this video, please be prepared to, switch between the YouTube tab, which is playing this video, and the other tab for lecturemate.site, where so that you can like cross-reference everything I say with the notes. Alright, so let's get right in. So the first type of question we will cover will be questions that deal with the comparison of atomic radius or things related to ionization energy. So you always get questions like explain the difference in ionic radius of Al3 plus compared to Mg2 plus. So as we all know, in the periodic table, Al is next to Mg, is to the right of Mg. So we have to follow this explanation for going across the period. So going across the period, of course, the electron shielding remains the same, but the positive nuclear charge increases, so the effective charge felt by the outer shell electrons is higher, causing the atomic radius to decrease. So in order to phrase our answer, I'll put it out like this. First off, you have to be very clear that you're going across the group, not down. This is very important to kind of set the stage. Then you have to talk about what changes. Going across the group, the positive nuclear charge would increase. Alright, but then you have to talk about what doesn't change. It's the shielding. The shielding remains the same. Good, now we've talked about whether we're going across or below. We talked about what changes and doesn't change, so now we have to talk about the consequences and how it leads to the ionic radius. So the consequences are electrostatic forces of attraction, nucleus and the So this word here, electrostatic forces, it's very important because it's basically a term just used to refer to the force between any positive or negative particle. And I've noticed that in quite a lot of the mark schemes, they actually like it if you say electrostatic forces of attraction rather than just saying nuclear attraction or whatnot, because it's more specific. So when it's possible to use this term electrostatic force, please use it. So easy. This is roughly 3 marks here. So for answering questions like this, first you have to state whether you're going across or down the group. This also applies to any other question where you have to compare things going down and across the group. Then you talk about what changes and what doesn't change, talk about the consequences, and lastly you conclude it. Alright, so the next type of question that we'll cover will be those that compare different melting and boiling points. So you either have questions asking you to compare two different two different chemicals with different melting points, or they will just give you one chemical and you have to talk about the melting point of that particular chemical. So in this case, we have to relate it to the structure and bonding. So as usual, for questions regarding melting and boiling point, they usually also require you to relate it to the structure and the bonding. So this is actually a very generic question. Okay, so first off, we have to see, is it a high melting point or a low melting point? So 109, okay, that is quite high. And then they're telling us that the molten compound conducts electricity. Alright, so we know that this is an ionic compound. So we have to explain why Bi2O3 is an ionic compound and how this relates to the melting point. So first off, I'll start off by explaining the structure and bonding of Bi2O3. So so first off, you basically just state what Bi2O3 is. Alright, after you've stated that it's an ionic compound, then now you have to explain why it's an ionic compound. Alright, oh by the way, I'm sorry, I also have to specify it's a giant ionic compound. So one thing is in Form 5 or in IGCSE, you only have to specify ionic or covalent, but in AS level, you have to be more specific. You have to specify alongside ionic or covalent, giant or simple. So giant compounds are very simple. They're crystals. They're things that can extend to infinity. Simple compounds are stuff like CO2, O2 that exist as separate molecules. So Bi2O3 is a giant ionic compound. Okay, we've already deduced the structure and the bonding. So now we have to explain why we think it's a giant ionic compound. Alright, so first off, the melting point. This is because Bi2O3 has a very high melting point due to the strong electrostatic twin. Alright, so basically, first off, I explain why it's a giant ionic compound from the melting point. Okay, and note that I use the term electrostatic forces. As I said earlier, please use this term whenever you can. Then now I have to talk about conducting electricity. So there we have it. We have basically our 2 marks. First off, for questions like this, you have to state the structure and bonding first. Don't care, you just state the structure and bonding. Then you explain why you think it is this giant ionic or a simple covalent or giant covalent based on the characteristics they give, which in this case is high melting point and can conduct electricity in a molten state. Alright, so let's take a look at this question. Oh, this is a question asking us to compare the boiling points. Also, okay, so this is also a variation of a comparison between melting and boiling point type of question. Alright, so first off, obviously it is going down group 14. And we can see that the boiling point is actually increasing. It's increasing quite steadily. Okay, so first off, we have to start off by defining what kind of particles these things are. Are they ionic compounds? Are they Are they, are they covalent compounds? Are they simple covalent? Are they giant covalent? All right. So in this case here, it is quite clear that CH4 is a simple. It is a simple covalent compound or simple molecule. SiH4 is more or less the same thing too. But it gets a little bit confusing when you go here because PbH4 is not exactly a simple compound. It's not exactly a simple molecule. However, they more or less follow the same trend. Okay, so first off, we have to decide what what type of molecule, what kind of particle all of these things are. I think let us just settle on calling them simple molecules. Okay. So we first state group 14 hydrides are simple molecules. Going down the group, okay, so going down the group, now we have to talk about what happens. Well, when you go down the group, basically what changes? The atomic radius changes. Alright, besides the atomic radius changing, what else actually also changes? The number of electrons actually changes. Okay, so when the number of electrons increases, then what does it do? It causes the van der Waals forces to be stronger. So basically I've talked about define what type of molecule they are, and then I talked about what changes as you go down the group. So if you notice, I didn't really write about what stays the same because that's not really relevant in this question. But if you want to write about what stays the same, you can. It's just that it may not give you any marks, but it may help to clarify things a little. Then we went on to talk about the consequences. The permanent dipole form is stronger. So permanent dipole forces increase going down the group. Alright, so now when we talk about higher melting point, we always have to talk about a melting or boiling point, you always have to talk about the energy. The van der Waals forces between the molecules. So the boiling point increases going down group 14. Done. Okay, so this is another one of those questions where we also have to compare the melting points or boiling points of two separate chemicals. In this case, it is phosphorus and sulfur. Okay, so for phosphorus, we see that its melting point is obviously lower than sulfur. and this is like pure solid phosphorus here and pure solid sulfur. So this is actually a bit of recap of the inorganic chapter. So you have to remember what phosphorus is in its solid state. It's in the form of P4. Sulfur in its solid state is in the form of S8. Alright, so first off we have to define what sulfur and phosphorus are. So in the solid states, P4 and S. Both simple molecules. Alright, but note here, sulfur, if we actually calculate the relative molecular mass of S8, it will be higher than P4. So therefore, we can also conclude that the number of electrons in S8 is more than P4. If you still do not understand this, basically you go to the periodic table and you total up the number of electrons for one S atom and then you times 8. Then you do the same for P4 and you'll see what I'm talking about. It will be like so much higher. Okay. Then, alright. So we'll have to talk about what is different between S8 and P4. So of course I've already talked about it, the number of electrons. Okay, so now we have to talk about the intermolecular force that is at play. So in this case, the intermolecular force that is at play would be not permanent dipole to permanent dipole forces, but rather London dispersion forces. Why? Because they are all the P4. I said they are pure, they are non-polar. So you have to talk about the instantaneous dipole. So therefore the London dispersion forces and as usual for any question with melting boiling point we end with this: more heat energy is required to overcome the between alright, done. Okay, so now we're going to move on to another type of question, which is about discrepancies in ionization energy. Okay, so you notice I basically just copied it over. This is because I've noticed that no matter what type of question they give, it doesn't really seem to matter how it's phrased, because for most of the questions I've seen regarding discrepancies in ionization energy, you're basically just writing the same points. So I would recommend just memorizing all of this. And if they ask something like, why does the ionization of energy drop from Mg to Al, then you just talk about these two points. Then if they're asking about why it drops from P to S, then you talk about these two, the spin pair repulsion and the electron being removed from a full orbital in S but half filled in P. No matter how they phrase the question, you're going to have to write down these facts. So sometimes they will actually attempt to like cheat you. So instead of giving Mg and Al, they will actually give you something like, why does the ionization energy drop from Be to B, from beryllium to boron. So don't worry, just write the same thing. It's the same thing still applies. Just it's just that rather than talking about the 3p shell, talk about the 2p shell. The trend will be the same regardless of the period. Okay, so the next type of question would be those where they ask you to describe observations. Alright, so first off, you have to figure out what is being produced. Okay. So in this case, HCl is added to a cup, and then they are adding Na2CO3 to it. So you are going to form NaCl and H2CO3. But note that NaCl and H2CO3, basically H2CO3 will break down into H2O and CO2. Okay, so normally when we have to describe a reaction, we will have to figure out what is being produced. Is it going to be a solid, a liquid, or a gas? So if a solid is formed, we'll usually say something like a blue solid, brown solid, orange solid, and so on. Orange precipitate. If it's a liquid form, we'll just say it is a blah 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 solution, blue solution, red solution, yellow solution, etc. etc. So you basically state the color and the state of matter, whether it's a solid, liquid, or a gas. So in this case, yes, we are producing NaCl and H2O, but both of these are like transparent. You can't really see. The only obvious thing we're producing would be CO2. So basically, when the reaction is being carried out, colorless gas bubbles will be released. But this question is a bit sneaky. Describe one observation that shows that the reaction is complete. So when a reaction is complete, there won't be any bubbling anymore. So you say color. So the answer would actually be colorless gas bubbles are no longer produced. Simple. So this is a bit of a twist on the question, but nonetheless it remains it remains roughly, you answer it roughly the same way. Right, let's take a look at another one. So in this case, you're adding AgNO3 to sodium chloride, NaCl, and then you add dilute NH3. Okay, so first off, you'll be basically creating AgCl and NaNO3. So basically the first thing, of course, AgCl we know is a solid. It is a rather dark solid, to be honest. So our first, so this I should move this here. So our first observation will be dark solid produced. Okay, so what happens next? What happens when we add NH3? Okay, so when you add dilute NH3, what will happen is that this NH3 actually, what it actually does is that it actually displaces Cl from AgCl. Oh, bruh, I should actually expand this a bit. Yep, displaces AgCl, displaces Cl from AgCl. So you will get Ag, pure Ag instead. So for pure silver, what you get a silver precipitate. Now this is just spatial for silver, but for others, like let's say if it's copper or iron, you can just say iron precipitate. Sorry, iron. I should not be saying silver. It should be more like silvery colored precipitate is formed. Yeah, this would be more specific. So for things like iron or copper, you just have to say things like dark precipitate form, brown precipitate form, etc. But for silver, you have to be careful lah, because you have to actually um when silver precipitate, of course it looks silver, it's like literally in the name, but you have to be more specific. In this particular case, silvery colored precipitate is formed. And also you may even want to write in some cases a silver mirror is formed if they are adding the full tolerance reagent. So just for Ag, you can actually say silver mirror is formed, but this only works for Ag. For any other metals, don't try this. For example, if you are precipitating out copper, don't say brown mirror is formed. No, it doesn't fly. Your silver mirror form only works for silver. Okay, so we will go on to the next type of question, where we will have to explain why something is a molecule and not an ionic compound, or why something is an ionic compound and not a molecule. So very simple. We actually take a look at whether it has high or low melting point, as I've written here, or whether it undergoes hydrolysis. Okay, so SiCl4. So the first question, actually we have to explain what happens when SiCl4 is added to water. So this is actually not really part of this number 5, but nevertheless I will be answering this question because it leads us to the next one. So when you add SiCl4 to water, the reaction is actually forms like SiO2 and HCl. So basically you have to say a quite solid is formed, that is SiO2, and HCl is released. How do you normally describe HCl? You describe it by saying steamy fumes. So this actually kind of leads to our previous type of question as well. And because SiCl4 reacts with water to form SiO2 and HCl, you can say that it actually hydrolyzes when you add water to it. So this basically proves that it is a molecule and not an ionic compound. Okay, so for the next question, yep, we have to use the melting point to explain why these have different structures and bonds. So as you can see here, SiCl4, we already know it is a simple molecule, but SiO2, not exactly an ionic compound. SiO2 is actually a giant covalent structure. Okay, so now we have to explain the difference between these two things based on their structure and bonding. Okay, so first off, we always have to state what type of molecule is what. So SiCl4 is a simple molecule. SiO2 is a giant covalent compound. Okay, then we have to talk about what's different. Okay. So because SiCl4 is a simple molecule, basically the forces that act between it are basically weak van der Waals forces, which are actually quite weak. So weak van der Then we have to talk about SiO2. So if you're not already familiar with this, SiO2 actually forms a giant structure that extends to infinity and held together by covalent bonds. So this is actually a very strong structure. Then, of course, with melting and boiling point, we always talk about the heat energy. You write our conclusion SiO2 is higher than, typo is higher than SiCl4 symbol. Now we got our marks for this. Okay, so since I've already been teaching for half an hour, let's take a short break for maybe 3 minutes, and I'll be back to continue the rest of this crash course. Okay, so I'm back, and let's continue with the rest of this speed run. So the next type of question would be reagents for organic reactions. So basically, for organic chemistry, for the organic chemistry chapters, there'll be a lot of questions asking you to state the reagent that you need to carry out a particular reaction. So I have basically listed out all of them here. And the questions are very straightforward. They are like, oh, we've got this reaction where we convert ethanol to ethanoic acid. So what reagent should we use? Basically, the questions will be more or less like that. Very simple, which is why I have not selected any of them here. So basically, try to memorize 1 to 12, all of this. I know it's not easy, but this is really important if you really want to get that A star. But note that for things such as oxidation, there are some discrepancies that, like for example, KMnO4. Basically, if you are just trying to get something from alcohol to an aldehyde, then you have to do oxidation with acidified aqueous KMnO4, under heating under distillation. If you want to get it all the way to ethanoic acid, then you have to use heating under reflux. So for oxidation, please be careful whether heating under reflux or heating distillation. And for reduction, also note that NaBH4 can only reduce aldehydes to alcohol. It cannot reduce carboxylic acids to aldehydes. So if you want to do that, you have to use LiAlH4. So NaBH4 can only do aldehydes to alcohols, whereas LiAlH4 can do acids to aldehydes and aldehydes to alcohols. As for the rest, there's not really much to say, it's quite straightforward. Okay, so now we go on to type 7, question type number 7, explaining why something becomes a major product. Okay, so first off, we had to talk about, the carbocation, then we had to talk about which is more stable, and then we explain why it's more stable, like in this case it's alkyl groups, and then we conclude. Okay, so when propene reacts with steam, alright, so propene will look something like, okay, I am lagging a little, something like this. So it can form either a propan 1-ol or propan 2-ol. Note that I didn't draw the hydrogen atoms here. This is mainly because I want to save time, and at this level you should already be able to kind of see where the hydrogen atoms are supposed to be. So basically it's like asking, why is this thing here the major product and not this thing? Alright, so first off we have to talk about primary to tertiary carbocations, etc. So first off, in this question, just to clarify things, I would have to state the products that are produced. So propan 1-ol and propan 2-ol are produced. So we talk propan 2-ol has a secondary carbocation. Okay. Then next we talk about the stability of the carbocations. And then we explain why. Because Okay, so of course we always explain it has more alkyl groups attached, but it'll also help if you go a little bit further and you talk about the electron releasing effect. Then we talk about how it's more stabilized. And then we lastly we conclude. Note that it's actually heavily recommended to write carbocation intermediate rather than just carbocation. And I'm sorry, I should have included that earlier on. Because saying carbocation intermediate, it is more accurate in a chemistry sense. If this is a little bit too difficult to see, I'll move it down here. Please pause the video and maybe read through this one more time if you need some extra help. Okay, so I'll go on to the next part, which is next type of question, which is talking about the reactivity of halogenal alkanes. Okay, so in this question, we have to describe and explain the trend of the reactivity of the different halogenal alkanes in this experiment. Okay, so obviously, time taken for precipitate to form. Alright, so the more time taken, then we can say that the longer it takes to react. So reactivity, so when it's longer time, then we can say it's lower reactivity. So this is least reactive, and this is the most reactive, 40 seconds, so it reacts really fast. So we have to describe and explain the trend in reactivity of the different halogenal alkanes shown in this experiment. Okay, so as we can see here, going down group 17, the reactivity actually increases. Okay, so as usual, when we are going down or going across the group, we have to state that. So going down group 17, the reactivity of halogens increases. Okay, so why? So going down the group, what changes? In this case, the atomic radius changes. It increases going down the group. So what is the consequence? Okay, so because it gets bigger and bigger, the nucleus of the halogen is further and further away from the shared electrons. So of course, the electrostatic forces of attraction will be weaker. So this is a bit of extra information. We can talk about the bond length increases. And when we're talking about reactivity, of course, we always want to talk about how the bond is broken, because reactions are about breaking bonds and forming bonds. And we can conclude that reactivity increases going down group 17. Okay, so we move on to the next type of question, which are basically questions about Le Chatelier's principle. So you will actually get quite a few of these. Okay, so for questions regarding Le Chatelier's principle, basically you just keep talking about whether the equilibrium shifts to the left or the right, and then talk about the backward reaction being exo endothermic, and then you can also talk in the case of gases where they are changing the pressure, you talk about the number of moles of gas on the right hand side or the left hand side. And then lastly, you conclude by saying the system moves to minimize the change. Okay, so if this sounds a bit abstract, then never mind. Let's put it to practice in a question. So in this case, right, so they are not actually changing the partial pressure of any of these. So they're just changing the total pressure at a constant temperature. So because they're talking about constant temperature, we don't talk about forward or backward reaction being exo and endothermic, because the temperature is the same, so this should not matter. Okay, so basically the pressure is increasing. So as you know, Le Chatelier's principle, they always want to minimize the change. So when they increase the pressure, they'll try to fight the change by decreasing the number of moles of gas. And we can see here that clearly there's more moles of gas on the left hand side. So basically you want to produce more SO3 and less SO2 and O2. Alright, so good, we've already more or less got our facts on hand. So first we have to determine, does it shift to the left or shift to the right? Okay, so as for rate and yield, okay, so I realized that I also have to explain what rate and yield is. So rate of reaction basically just refers to like how many of the SO2 and O2 react per second. Yield refers to what percentage of the product exists. So they are not the same. You can have SO2 and O2 reacting at a very high rate, but only 20% of the equilibrium solution or equilibrium gas is SO3. You can have them reacting very slowly, but have like 90% of SO3 in the composition. So there are two different things. Yield is just like basically what's the percentage of SO3. Rate is like what's the actual raw rate of production of SO3. So anyway, so we'll talk about the yield first. So anyway, because you increase the pressure, it wants to fight the change by reducing the number of particles. So equilibrium shifts to the right because there's less number of gas on this side than in this side. So first you have to say equilibrium shifts to the right. Okay, then why does it shift to the right? This is because the number of particles on the right hand side. Please write this in full, but I'm just writing it in the abbreviation so that it's easier. So lastly, we talk about how this happens to fight the change. Right. So now let's talk about the rate. Okay, so yield basically is about the equilibrium. So when you answer questions about the yield, talk about equilibrium. When you answer questions about the rate, this is not really about the equilibrium. This is about the rate of reaction, the kinetic theory, that kind of thing. So when you so rate, how does it increase the pressure? Okay, so when you the pressure is increased per unit volume increases. Alright, simple. When you're talking about the rate, as I've said earlier, it doesn't refer to the percentage of SO3 or the proportion of SO3 that is present in the equilibrium mixture. It's just talking about the raw rate of production of SO3. So your equilibrium doesn't matter. What really matters is the pure rate of reaction. So when you answer questions regarding the rate, answer it based on the rate of reaction stuff. When it's about the yield, talk about the equilibrium, the Le Chatelier's principle. Okay, so next, questions about catalysts. So you'll always be asked to describe how a catalyst affects a reaction and why something is a catalyst. So basically, in AS level, you only you you'll mostly be dealing with homogeneous catalysts. Basically catalysts that are the same phase as the same state as their reactants. So if their reactants are liquid, the catalyst is also liquid. So a catalyst, as we know, they increase the rate of reaction. So how do they increase the rate of reaction? They increase it by offering an alternative reaction pathway of lower energy. Of lower activation. And when they lower the activation energy, the frequency of effective collision actually increases. I should phrase this better, to increase. So this is basically how homogeneous catalysts affect a reaction. Heterogeneous catalysts will affect the reaction, they will increase the rate of reaction in another way, but you don't really have to learn this until you get to A2. So for now, just remember this explanation, offering an alternative pathway, lower activation energy, and so on. And now you have to explain why H3PO4 is a catalyst. Okay, because you're only dealing with homogeneous catalysts, very simple. Two things. Number one, H3PO4 offers an alternative reaction pathway for lower activation energy, and this is very important, is regenerated. This keyword is very important. It is regenerated. Okay, so let's go on to the next part, which is about hybridization. Alright, so this one just a quick, okay, for question 1, I'm just going to draw out the formula. I'm not going to actually, I'm not going to actually draw the dot and cross diagram because that's not really what we are trying to answer today. So basically the N2F2 look like this. Sorry for the bad handwriting because I'm not good at drawing with a mouse. So it'll basically look at like this. Single bond have an N, single bond have an N, and double bond between the two ends. I think I should maybe change this up a little. Yeah. So double bond here, single bond here. So describe the hybridization of N atoms in N2F2. Okay. So hybridization, so it's very simple. Single bonds sp3, double bonds sp2, triple bonds sp. So simple. We just say the N atoms, they have double bonds here. So that means have NsP2 hybridization because they have one double bond each. Simple. Okay, so next will be about stereoisomers. Alright, so with stereoisomers, there are two types of questions. The first type is where they'll just like give us something, like in this case it's an unbranched hydrocarbon, and then they'll just ask us like, oh, okay, why does it show stereoisomerism? Another type is where they'll give us a reaction and then they'll ask us to explain why the products are stereoisomers. So for the first type of question, I've actually provided an example here. Unbranched hydrocarbon that causes its molecules to show stereoisomerism. Okay, so the question is a bit it's like kind of incomplete here. Okay, but if you actually checked back at the previous sub questions, then basically they'll be talking about double bonds. Alright, so think about it this way. The unbranched hydrocarbon they're talking about is one that actually has double bonds here. So let's think about the types of stereoisomerism. We have optical and geometrical isomerism. So as we know, geometrical isomerism is when you have two different groups on sides of the carbon atom. Optical is when you have one, like basically one carbon atom with attached to four different groups. So double bonds, when you see double bonds, then the first thing you think of is of course geometrical isomerism or cis-trans isomerism. So basically you just start off by saying the unbranched has a double bond which is attached to different groups attached to, this is very important, both carbon atoms in the C double bond C bond. This is important because if only one side is attached to two different groups, you don't have cis-trans isomerism. Then you have to further explain. you have to talk about why the double bond cannot rotate and that it will result in two isomers. So basically, for stereoisomerism, there are two types. It's optical, it's geometrical. Usually, if it's in the context of a reaction that produces something with chiral center, then you talk about optical. If it's something involving double bond, talk about geometrical or cis-trans. The explanation I gave is for the one for cis-trans isomers. Yep, I apologize. I should have also included one for. Oh yeah, I did include one for geometric isomers down below. Sorry about that. Yep. So when you have to explain why something is a stereoisomer or a geometric isomer, you just follow the two explanations I gave right here. Yep, and this is another. Yep, this is an kind of another. Yep, extension of the question here. Alright, so now we are more or less on to the last few parts, which is about the IR spectra. Alright, this is, I think, yep, this is the last slide. Okay, so for questions regarding IR spectra, there are two types. One type is I will call it the easy type. They'll just give you a spectrum and then they are going to ask you, oh, give me the functional group and explain why. Alright, for these types of questions, they are really simple. All you have to do is to basically state what bonds it has and then state what peak it has. So functional group, alright, let's take a look at this. Seems to have a peak between like 1700. 1710 to 1617. Yep, 1710 to 1750. What do we have in this range? So we have what appears to be an ester. Do we have any more clues? Let's look at the. Okay, we seem to have one between 2850 to 2, but this just appears to be alkane. So basically what we have here is mostly an ester group and an alkane group. Okay, so the functional group present, we'll just say it is an ester group. Why? Simple, we just state the DIR spectra. Alright, so we just state the group, which in this case is an ester group, and then we talk about and we explain. So first we have to state what the range of the peak is, and then we have to say it corresponds to the IR absorption range for the something bond in the group. So this is important. We have to state the peak range, the bond that is involved, in this case the CO, and the group, which in this case is the ester group. So you might be saying, okay, ester groups also have an absorption in 104 or to 1300. So why don't we talk about that? This is mostly because below 1500, it is very hard to read the graph. And so usually I would choose to talk about things above 1500. But if they ask for longer explanations, I will also try to include stuff here. Alright, so now we move on to the second part of basically the second type of question for IR spectra, where they will like tell us a reaction where you have D, which is reacting with sulfuric acid to become E, and then how the infrared absorption range will change. Alright, so this is a bit tricky. First off, we have to determine what will be different between the infrared absorption range here and here. Okay, so here as you can see, we have OH groups. We don't have them here. So basically the hydroxy group 3200 to 3260, 3260 are going to go away. Then what other differences are we going to have? The CO will also start to shift from 17 this range to this range. Why? Because it goes from being like in a carboxyl group to being in a being in an ester group. Okay, so first off we talk about the OH bonds. So the peak at 320 disappear. Okay, this is so we also have to, just for clarity, we also have to explain what corresponds to corresponding to the OH bond will disappear. So this is because it does not contain any OH groups. Okay, then what's the second point? The peak at 1670 to 1740 will shift. Alright, in this case it will shift to the left because 1674 1740 is here, 1710 to 1740 is here, so like it shifts, so it will shift to the left. So basically, alright, if let's say if it's the same bond but it changes functional group, you have to explain that it shifts to the left or the right. But if the bond is basically disappearing entirely like OH, just say that it disappears. As usual, I talk about the bond it is corresponds to. Right, so basically this is how we answer these kind of questions. Basically we talk about we figure out what changes, and then we write, okay, the bond will disappear or it will appear. The bond, sorry, the peak at blah 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 and blah 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 corresponding to what bond will appear or disappear, because D has something, E does not have something, or D does not have something, E has something. Then we can also talk about the peak if like it's the same bond but they are changing groups, like the CO bond here being in a carboxyl, CO bond here is in an ester. Then we will have to say that it shifts to the left or to the right because D has carboxyl, E has ester, or vice versa. So all in all, this is basically all I have to teach for AS chemistry. Of course, there are many other types of questions, some rarer types that I have not covered. because they are not repeated very often. So I hope that this session has been very helpful to you. If you have any questions, please let let us know in the comments, and make sure to share this video if you have found it to be very useful. Thank you for listening, and God bless.